Hi, in this video we'll be continuing the study of rings, and right now what we want to talk about is the rings of fractions. So how we from one ring we can get more rings. So it's building upon what we have. So what we have is we have a ring, then we can build more rings by taking the sum, the product, the quotient with an ideal. And now what we do is we can create a ring by creating this thing called the ring of fractions. And so in this section we assume that the ring is commutative to avoid all the troublesome details. And we already see that if we know that A is not 0 or not a zero divisor, then the cancellation laws apply. And thus, a non-zero element that is not a zero divisor enjoys some properties of a unit. Because if A was a unit, then you can just multiply by the unit and you get the same result where B equals to C if you see. So, and we already know that the non-zero divisors cannot be a unit as we have proven earlier. And so, if A is a zero divisor, then we cannot always cancel the equation to obtain B equals to C. And this gives us a understanding that there is some form of relation that we can try to get from the units and the zero divisor and the non-zero divisors. And so, we want to prove that a commutative ring can be always a subring of this larger ring Q, in which every non-zero element of R is not a zero there is not a zero divisor. So the non-zero divisors in R is a unit in Q. So you're really creating a larger ring in which we say that all the non-zero divisors in R is a unit in Q. And this ring, we now call it, will be no if R was an integral domain, then this ring that we created will be a field, and it's really called the field of fractions. And indeed, was really basically a generalization of how you constructed the rationals from the integral domain of integers. So that's why rationals be considered a field, and as the field properties. And as a result, we just need to look through the proof of the rationals from constructions from the integers, and we are able to generalize them to the field of fractions. So how do we construct the rationals from the integers? Well, we need to define an equivalence relation where two fractions are the same if and only if AB equals to BC. And so this really forms a class or equivalence classes, and we can then define the arithmetic fractions operations as the following, like we always know. And actually this can be checked to be well defined, and it actually makes the set of fractions a commutative ring. And in fact, we already proved that this commutative ring will have multiplicative inverses. And so how do we do that is that we need to argue, we just need to check that it's commutative, and so. And then the integers will then be a subring of this Q, which can be identified by dividing by 1. And it has an inverse, so it's a unit. So you can see that we have created what we want to have. So these are the properties we want to have, so we have already constructed it. And so it's reasonable to do the same steps to create for arbitrary commutative ring. But if you were to take an arbitrary commutative ring, then you run into what happening if B has a zero divisor and stuff. And then it takes a little bit more effort to play with these details, which we'll go into in a short while. But you realize that it won't be a field anymore, but instead be a ring. Only a ring. And so now, let's construct from a general ring, a ring of fractions. And so we let D be any non-empty subset of R that does not contain zero. Does not contain any zero divisors and is closed under multiplication. So D is like your set of denominators that you want. So in these denominators, we impose some conditions that it does not contain any zero divisors. But you can see R has no conditions in this case when you already impose conditions on the denominators. And so R can be just any commutative ring. And then we say that when you do that, then there is a commutative ring Q with now an identity even, such that R is a subring of Q and every element of D is a unit in Q. And the ring of Q has the following properties, where every element is of the form R times R over D basically, so it's R times D inverse. And in particular, if D is equals to R minus with 0, then Q is a field. So what it really means, if D is the set is R minus 0, it means that R is an integral domain since it does not contain any zero divisors, and thus Q is a field. And the uniqueness just follows from the commutative diagram argument that is very standard. And after this, we see that we can actually generalize this even further. And so the way you construct this and you prove the following property is exactly the same as when you did it from integers to rationals, so I won't go through it. But the main idea is, of course, to create the equivalence class using this same property. And this ring we will call the ring of fractions of the denominators. And the usual notation is this. And if R is an integral domain, then D will of course be D R minus 0. Then Q will be called the field of fractions. And so if R is an integral domain and Q is the field of fraction, then any other field containing this subring R prime, which is isomorphic to R, then the subfield of F generated by R prime will be isomorphic to Q. So it's really just a commutative diagram where you go R to Q, R prime to this Q prime, and then you can go R to, and then because these two are isomorphic, you get to isomorphic the Q to Q prime. So this Q prime lies within F, and similarly this Q lies within F. So you're done. So really what we want to take a note is some examples of if R is a field, then the field of fraction of course is just R itself by this corollary. Z being an integral domain, the field of fraction will be the field of rational numbers. And if you just take, you can see this example, which is very interesting. It says that if you take a subring, which is just the even integers, it doesn't have any zero divisors, but it also has no identity. Then its field of fraction will also be the rationals, and you can check that. And you can see now how in the rationals the identity appears because it's just 2 divided by 2. But in the earlier subring, there is no identity. And so the last part, we'll just talk about the Chinese remainder theorem to wrap up this part of the section before moving on to Euclidean domains in the next video. And so for the Chinese remainder theorem, it's really, first we need to define what coprime ideals mean. So two ideals are coprime if when you take the sum of them, it equals to the entire ring. And this is really the generalization of coprime integers, because coprime integers means that you can find this a solution to this equation, nx plus my equals to 1. And if you to take the ideal version of stating this in terms of ideals, this is just means the ideal of n plus the ideal of m equals to the ideal of 1. But the ideal of 1 equals to r. And the ideal of n is just nz. And this is just mz. So multiples of n plus the multiples of n will equals to the entire of r, which in this case is z. So you can see that how the equivalence between this coprime meaning and coprime in the sense of integers. And so the proof of the Chinese remainder theorem is just a basic checking using the isomorphisms theorem. So you basically have an ideal, and then the map from R to this the quotient multiplied with each other. So you go to R quotient A1 times R quotient A2 all the way, and then you just define it to be R, and then you just send into each coset. And this is actually a ring homomorphism with the kernel as the intersection of everything. And so by the first isomorphism theorem, you just take you can actually just show that R over when you multiply all these coprime ideals together, it equals to R over this intersection, which then has to be isomorphic to the image. And the image is surjective, so it's just the whole codomain. And as a result of that, you can actually see how this leads us to be able to factorize the quotient ring of z over nz, where n is this prime factorization, and so you can factor it into each prime ideals. And then we have in particular the units of this ring will just be the units multiplied to one another, because it's a ring homomorphism. So the Chinese remainder stated in the general sense is as follows. And if you were to compare this with, of course, in the integer sense, you just need to replace this with the primes, and you'll be actually getting the same exact answer. And if we compare the orders, then the order of this side is phi of n, and the orders of this side are just the phi of p1 alpha 1. Then since it's multiply, you just need to multiply, where phi is the Euler torsion function. And because of that, you can actually see that the value of phi on the prime powers of p alpha is p to the power alpha minus 1 times p minus 1. And you can actually find a formula for phi of n as a result. So what we really want to note is we want to use the Chinese remainder theorems to solve systems of congruence equations. And one thing is, of course, now reformulated, we can actually just see that the Chinese remainder theorem can be restated as the following. As that for any k integers, there is a unique solution somehow to the simultaneous congruence equation, where x is congruent to A1 mod M1 congruent to A2 mod N2, and so on. And that the solution of X is unique mod N, where N equals to N1 times all the way to Nk. So this is really a special case, so I'll let you do it yourself by just applying the general Chinese remainder theorem. But for part B, we want to actually show that the solution is this form. And it's just a step of verification, so you just let the solution be what you thought of. And you just let X equals to A1 plus all the way to AK plus TK NK prime plus P times N, because this is mod N. So then you just take mod Ni. Well, N has contained Ni, so this part cancels. Then all the other parts that have an Ni will cancel. And so what you're left with is the only part where Ni prime, you have Ni prime, because Ni prime is defined to be N over Ni. So you take out so you have N, and N has the factor Ni. Then you take away Ni, so all here don't remain, are all co-prime to Ni already. So you're only left with this term. And because Tj is the multiplicative inverse of Ni prime, as what we have defined. So this part is 1, so it's just you're left with only Ai in the end. So X is co-prime to Ai mod Ni for all i's. So it actually is a solution to the system that you want, system of equations that you want. So we have verified that this is the solution, and it is unique based on what we have proven in part A, because by the Chinese remainder theorem. So you can see how finding a constructive proof may not show that it's unique, but we've proven it in a non-constructive way to be unique using the isomorphism theorems. And so now we want to really use what we have to prove and solve system of congruence equations. So let's just say we have the congruence equation x2 x3, x is mod 2 is congruent to 2 mod 7. So like the following way of doing this, we need to first find the inverse of Ni prime for each I. So and I is just Ni prime is N over Ni. So first one is for mod 3, you just need to take, so it's your N in this case equals to 3 times 5 times 7. For mod 3, you just need to divide this away. It's N over 3, so that's just 5 times 7, which is 35. And then you mod 3 it, and you get that its inverse, the multiplicative inverse is -1. Similarly, for 3 times 7 is 21, and you see that the multiplicative inverse is 1, as 21 times 1 equals to 1 mod 5. And similarly for 15, the multiplicative inverse is 1 as well. And so the solution, you just need to apply it, is the coefficient 2 times -1 times 35 plus 3 times 21 times 1 plus 2 times 15 times 1. And when you sum them all up, you actually get 23 mod 105. And you're done. So I hope this example shows you how you want to apply the Chinese remainder to solving questions about congruence equations. That's all for this video, where I wrap up an introduction to rings, where in the next video I'll introduce more types of rings where we put in more structure. So I'll catch you in the next one. Bye!